Now, in this video, we'll be talking about the time-dependent perturbation theory. In quantum mechanics, time-dependent perturbation theory is a mathematical tool used to calculate approximate solutions for a physical system under the influence of an external time-dependent forces. And and when we talk about this time-dependent perturbation theory, we straightforwardly talk about Fermi golden rule. And this Fermi golden rule is a formula basically that's derived from this theory that calculates the transition rates between different quantum states. Now, this time-dependent perturbation theory, this method is useful. It's very useful in scattering theory problems involving radiation absorption and emission and various field theoretical problems. It's based on the idea of basically starting with a sample system. And this sample system is chosen as a starting point with a known solution, and then adding a perturbing Hamiltonian to represent a weak disturbance to this system. And in talking more about this Fermi golden rule, this rule describes the transition rate. What it does basically on making calculations, what it does, we are able to describe the transition rates from one energy eigenstate to a group of energy eigenstates in a continuum that are caused by a weak perturbation. This Fermi golden rule is applicable to situations where the final state is discrete with some kind of decoherence in the process. The rule is used in various fields. It's used probably in nuclear physics. It's used in optics, and broadly used in quantum chemistry. It's also crucial for understanding the noise that arises in electronic devices like transistors and p-n junctions. Uh, and uh, and in this video, we will be discussing, we will take the theoretical structure of this time-dependent perturbation theory, and then this perturbation theory will lead to this Fermi golden rule, by virtue of which we can be in a position to calculate all. So, hello, dear students, dear friends. In this video, I'll be talking about time-dependent perturbation theory, and the motivation of deliberating this video is to have some insight into the application of this time-dependent perturbation theory, and automatically it will lead to Fermi golden rule, and it will certainly be a starting point for understanding the phenomenon like Raman effect. Now, as we know that this time-independent perturbation theory, uh, uh, which was developed by Schrödinger, it applies only for isolated systems, and I should say for which the Hamiltonian is independent of time. So this Hamiltonian is independent of time. So this is what is our time-independent perturbation theory. And for such a system, the energy states are these energy states are stationary, and the time enters only in phases, uh, and the probability of finding an eigenvalue in a measurement of energy is constant. Now, if an external force, you have a system, so time independent is it's a basis to understand the systems which are idle, and there's no interaction with the system.
Now, if we have an external thing, say some kind of force, now this external force is, if this external force is acting on this system, the situation is changed now. And why is it changed? It's changed because the Hamiltonian of this system contains a time-dependent part, and representing the external influence to this system. And automatically the energy eigenstates, they also depend upon the time, in amplitude as well as in phase. So time comes in picture here. And, and in order to study such cases, there is another perturbation theory, and this perturbation theory is known as time-dependent perturbation theory. And so, in this case, what we attain basically is the probability of the transition. So what we have here is probability of transition of the system from the unperturbed state. So suppose there is a state which is unperturbed to a perturbed state. And this transition that takes place, say for example a transition of an electron from one energy level to another energy level, this transition to another state is a result of the perturbation. And a few of the results of this time-dependent perturbation theory can be managed by making use of Fermi golden rule. And this Fermi golden rule provides the background. It provides a background for a quantum mechanical description of Raman effect. And the most important case that we can think about, the most important case of interest is the one where we have the external sinusoidal fields. And these external sinusoidal field is a sinusoidal function of time. And for most of the practical applications, the external fields are sufficiently weak. So the field that's interacting with the system, these fields are weak. They're weak. And we can say, so we can say that their effects can be handled. The effects of these weak fields that are interacting with the system, these effects can be handled within the framework of perturbation theory, where the unperturbed wave function serves as a basis. It serves as a basis for describing the perturbed system. Now, if the perturbation has an explicit time dependence, it must be handled by time-dependent perturbation theory. So we can start here with the time-dependent Schrödinger equation, and we can put on the terms that are linked as the unperturbed and the perturbed Hamiltonians. So if I write down the time-dependent Schrödinger equation for such a system where there's a perturbation that's acting on the system. So writing down the time-dependent Schrödinger's equation, psi by dou t is h psi. Now this h can be chosen as h naught plus h dash of t. So this h dash of t is the time-dependent perturbation. And what we do then is that we then expand this time-dependent wave function, psi, which is a function of both r and t. We expand this wave function in terms of complete set of eigenfunctions of this h naught. And to move on from here, what we see is we'll take on this psi as psi of t as sigma an of t, phi n of r, and e to the power of minus en t by h cross. where uh, this an of t is the time dependent constant. That will be precise. It's time dependent constant. This phi n of r, this term, this phi n of r is, this is the time independent constant. Time independent constant. And what we can do is we would like to substitute this psi, this wave function, into the Schrodinger's equation. So here we have Schrodinger's equation. So this is equal to, instead of h, we have h naught plus h dash of t, of psi. All right. So for that, what should we do is we have to substitute this wave function in this equation. All right. And we can see, okay, so we will have I h cross dou by dou t sigma a n of t phi n of r e to the power of minus e n t by h cross is equal to h naught plus h dash times psi. So psi is sigma a n of t phi n of r e to the power of minus e n of t by h bar. All right. So what we have to do here is say a n of t is a function of time, and this exponential function is the function of time. So we got to differentiate the two functions. So we will have UV rule between a n of t and this exponential function. This phi n of r is constant, so it can be taken outside this differentiation. So and what we'll do after that is we'll take on these independent terms. H naught will be multiplied with this, and h dash will be multiplied with this. So in doing so, what will I have is I h cross. So let's use some bracket. So what I will have is I would like to differentiate this first. So if I differentiate this, its differentiation will be a n of t. I'll put a dot on it. So I have differentiated this, and the exponential function will remain like this, minus e to the power of e n of t by h cross. And at the same time, phi n of r will remain like a number because it's a constant. And here I'm missing something. I have iota here. How I put it here? Yeah. So here it is iota. Okay. So here it's iota. So here it's iota. Okay, so then we will have plus a n of t as its, phi n of r will remain as its, and then the differentiation of this will give me, minus I e n by h cross, and the exponential function will remain like this. So this bracket can be closed. So we have differentiated this set of functions, and this is equal to, so this h naught will be multiplied to this, so we will have sigma n a n of t, then I'll have h naught phi n of r e to the power of minus e n, this is iota e n t by h cross. And then we will have another term for h dash, that is plus sigma a n of t h dash phi n of r e to the power of minus iota e n of t by h cross. All right. Now, what we would like to see here is that that we have a term here. We have a term for unperturbed. If I have to write down the Hamiltonian for unperturbed, what will be that? That will be h naught of psi is e n of psi. So that thing will be applicable here. So here I can write down En instead of h naught. I can write down here En. So if I write down here En, this term and this term, if we rightly look at this term, so here it is En. Okay. Yeah. So in this case, what we will have is if I take iota h cross inside, this iota and iota will die because they will make iota square. So that will be -1, minus minus will be plus. So this will be plus. It will be a n of t phi n of r e n e to the power of minus iota e n of t by h cross. And this term, and if you will rightly look at it, and using this equation and this term, these two terms are identical. And if they are identical, we can cancel these two terms, because instead of h naught, we are going to use en. So this term and this term will be cancelled. So when these two terms will be cancelled, we'll be left with, what we'll be left with, we'll be left with this term, and we'll be left with this term. So let's write down these two terms so I can see it. So we will be left with sigma n. So iota h cross is there. Then we have a dot of n of t phi n of r e to the power of minus e iota en t by h cross. This is going to be equal to sigma a n of t h dash phi n of r e to the power of minus iota en t by h cross. Now, if we rightly look at this equation and we multiply this equation by phi, multiplying both sides by phi m star and integrating over d tau, or the volume theta. So what we will have here, we will have sigma n I h cross, and what will be out, I think this phi n of r will be out. It will be out. No, this a dot n of t, a dot n of t will be out. E to the power of minus iota en t by h cross will be out, and the integral phi m star of r and phi n of r d tau. This will give us, so what will be out here, we will have a n of t and e to the power of minus iota en t by h cross, and integral, okay, again we'll have phi m star of r and h dash, okay, we have the perturbed Hamiltonian, and phi n of r, then d tau. And in this, we can proceed from this equation by using the condition of orthonormality. Now, what is the condition of orthonormality? The condition of orthonormality is that this integral phi m star phi n, both functions of r, d tau, this will give us 0 for n is not equal to m, and this will give us 1 for m is equal to n. So all other values are going to vanish for n is not equal to m, and we'll be left with a value equal to 1 for n is equal to m. So what we can do here is that when we will use this condition of orthonormality, so the left-hand side will exist only for n is equal to m. So we can change the nomenclature here for the left-hand side, and using the condition of orthonormality, what we will write is, we'll write sigma n I h cross a n dot of t e to the power of minus iota e m t by h cross, and for the integral we'll just write delta n m, and this will be equal to sigma a n of t e to the power of minus iota e n t by h cross. And when we have used the condition of orthonormality here, so this left-hand side is defined for only one value. And what is that value is for n is equal to m. So we can write down this an, because this whole thing can exist for the single value. So this an will change to am. And I can write down this a m dot is 1 by I h bar sigma a n of t. And the integral that we have here, this integral is the matrix element. So I can write down this integral in terms of the matrix element. So what will be that? That will be m h dash n. So this is the matrix element for this perturbation Hamiltonian. And then we will have e to the power of iota. Okay, so this will come this side, so you will have iota times em minus en times t by h cross. So this will be the amplitude. This will be a dot m of t. So this is going to be a dot m of t. Now, proceeding from here, we can write down this equation in a little more compact form. And what will be that? So I can write down this. So what is this a m of t here? It is they are the time dependent expansion coefficients. They are the time dependent expansion coefficients. Uh, uh, and uh, and and we can compress this equation, and we can write down a dot m of t is equal to 1 by I h cross sigma a n of t, and then e to the power of iota omega m n t, and the matrix element m h dash n. Right. And what is this omega n here, mn? This omega mn is Bohr frequency. Call it Bohr frequency. And this Bohr frequency is proportional to the difference in energy between the state m and n. And we can write down this omega mn equal to em minus en by h bar. And this matrix element is already defined. It's there, and we can write down this if you are interested. This matrix element m h dash n is nothing but the integral phi m star of r h dash phi n of r and theta. All right. Now, since this h dash, this is time dependent. It depends on time. So to our the matrix elements, they are also dependent on time. And in applying perturbation theory, what we do is we consider this matrix element that we have to be very small. And what we do is we write each time dependent amplitude as an expansion in perturbation theory. So if I take an example, if I stand am as am, say for example am0 plus am1 plus so on and so forth, and this gives me sigma I running from 0 to infinity, am raised 1. Now, what am I trying to say here is that this superscript I that is here, or I can put it in this summation, this is I here. Okay, it gives the order of each term in perturbation theory. Thus, if I talk about am0, this is the zeroth order term. And if I talk about am1, it is the, if I go with ami, it's giving me ith order correction to an. So we can see that this am of t that we have, am of t that we started with, this am of t changes its value with time only because of time dependent perturbation. Thus we have the unperturbed situation for this zeroth order it's a representative of unperturbed situation. And this zeroth order perturbation theory must give no dependence, no time dependence in zeroth order, and has values only for the initial state, and has values in a state in which this unperturbed situation arises. Now, then, where from the correction starts? The correction will start from AM. If I take on the first order correction, that will be AM dot 1, that will be 1 IH cross sigma AN of 0, the matrix element M, H dash, and N, e to the power of I omega MN T. And this will be equal to 1 by IH cross to a state AL 0 M H dash L e to the power of I omega MN T. So, so this is our first order correction that we can think about here. Now, for the sake of interest and for the sake of our interest here, if the perturbation H dash has sinusoidal time dependence, sinusoidal time dependence with some frequency omega, which is a situation of all resonance phenomenon, we can write down this H dash as H dash of 0 e to the power of plus minus I omega t. And this certainly does show the explicit time dependence of the Hamiltonian, so that upon integration, when we integrate, I mean, when we carry out the integration of this equation, when we carry out the integration of this equation and we do some manipulations of the terms, what we do is we obtain the probability of finding an electron in a state M. And certainly we know that when we take when we take this, say, AM1 of t, the square of this amplitude gives us the probability density, and this probability density comes out to be the matrix. It has to be the square of M H dash L whole square divided by H cross square 4 sine square omega M L plus minus omega times t by 2 divided by omega ML plus minus omega whole square for M not equal to L. And this is the crazy equation that we obtain when we do these manipulations that I was talking about. I mean, after carrying out the integration to the amplitude and then having a little bit of manipulation, what we do is we obtain the probability density. We obtain the expression for probability for finding an electron in the state M. And this omega is the applied frequency that we have here. This omega is applied frequency. And this omega ML, this is resonant frequency. For the transition, so this is the term that carries a process of transition. And here the explicit time dependence is contained in this oscillatory term. And this oscillatory term can be thought in terms of this sinusoidal function. And we can boil down this, we can put this omega ML plus minus omega, if we take this equal to, say, omega dash, suppose this omega ML plus minus omega is omega dash. So we can boil down this equation to AM1, which is certainly the function of time whole square. We can think of it as M H dash L whole square by by h cross square 4 sine square omega omega dash t by 2 divide by omega dash square. All right. Now, since this is our probability of finding the electron, and since this transition probability that we have here, it is proportional to time. So it's therefore important to introduce the quantity that's called as transition probability. Transition probability per unit time. And the relation that gives this quantity, the transition probability per unit time, because we can see that this probability of finding this electron is proportional to the time. So we call this thing as transition probability per unit time. And this, the calculation of this transition probability per unit time is called Fermi golden rule. So this is what is called Fermi golden rule. And certainly this Fermi golden rule has been there for the name of it's named for Enrico Fermi, who first introduced this rule to calculate such kind of transition probabilities. And we can sketch down this in a graph. If I take a rough note of it, we'll try to draw it. Say this is omega dash, and here we have. So this is my 0, this is minus 2 pi by t, this is minus 4 pi by t, and this is minus 6 pi by t. So this is 2 pi by t, this is 4 pi by t, and this is 6 pi by t, and here we have 1 by 4 t square dependence, and this is my sine square omega dash t by 2 divided by omega dash square. So what we have here is we have a plot between this function and omega dash, and a function which enters the calculation of the typical time dependent perturbation problem. Now, proceeding from here, now in deriving this Fermi golden rule, what is important here is that we consider the system to be exposed to the perturbation for a time sufficiently long. So we perturb the system, and we assume that this perturbation is exposed, it's entangled for the time sufficiently long, so that we can make some meaningful measurements within the framework of Heisenberg's uncertainty principle. And what is Heisenberg's uncertainty principle? It is delta E, and delta T is of the order of this h bar. And so that this uncertainty in energy, or because energy is connected with the frequency, during the time that the perturbation acts, so it will be delta E is nearly h by t. Or we can think of this delta omega Lm of the order of 2 pi by t. And we can see here this is precisely the period of oscillatory function. If you look closely on this approximation, and in this context, what we do is we think about the concept of transition probability per unit time as comprising a range of energies and times, and all these ranges of energies and times happen to be consistent. They have to be consistent with what we call as uncertainty principle. Now, if we take on the example of, say, for example, if we think about a solid. Now, in case of solid, it's quite natural to do this in any case, because the wave vector k. If we think of a solid, if we think in terms of the wave vector k, this k is a quasi-continuous variable. It's a quasi-continuous variable. And that's there are a large number of these K states which have energies very, very close to the given energy. And since the quantum states that are labeled by this vector K, they are close together in the solid, and the solid having of the order of 10 to the power of 22 atoms per centimeter cube. And we can think in terms of the photon source itself as a bandwidth, and we would automatically want to consider a range of energy difference, of the order of say h cross del omega dash, that we are noting down. Now, from this point of view, what we try to do is we introduce this transition probability per unit time. And for the sake of having this transition in case space, where you have large number of levels closely packed. Say, if we think in terms of a solid, say insulator, it has valence band and it has conduction band. So this kind of thing can be thought of, and in doing so, what is done here is that we introduce the concept of transition probability per unit time, and this transition probability per unit time is symbolized as WM. So this is transition probability per unit time. And this Wm is 1 by T sigma Am1 of T whole square. And this summation is carried over all range of energies, that are consistent. Say, taking some m dash very close to some n, uh, and uh, and consistent with Heisenberg's uncertainty principle, so that this delta omega m dash is nearly 2 pi by t. And if we substitute for am of t from the equation that we have this am1 of t whole square. It's here. Where is it? Here. Okay, here. In terms of omega dash, because omega dash is taken out equal to omega ml minus omega. So we can do that, and we can write down this. What is that? Am of t. We can write down this Wm, and what it comes out is it is 4 by h cross square t integral h ml dash sine square omega ml t by 2 by omega ml square, and multiplied by rho em dash and dem dash. And what we have done basically is that we have replaced the summation that exists in this equation by an integration over a narrow range of energies that are weighted by the term density of states, that is rho em dash, which denotes the number of states per unit energy range. And this h dash ml, this h dash ml is written for the matrix element. And what was that matrix element? It was, if I take it as m dash, h dash, and l. And at the same time, if we think in terms of the if we think in terms of hypothesizing our problem, but we are only considering the energies within the small energy range. The energy range that we are taking into account is extremely small. That's em dash, and this em dash is around em energy states. And over this range, the matrix element and this is my matrix element, and the density of final states, the density of final states will not be rapidly varying, will not be varying much. However, the function that's here in terms of sign, this function will be varying rapidly. And as we can also see it from the graph that we have drawn, we can see that this sine square omega dash t by 2 by omega dash square, it's varying very rapidly. Therefore, it is plausible. It's plausible to integrate this equation over the rapidly varying function, and getting out the matrix element and the density of states outside this integral, and keeping only this sinusoidal function, and looking for its integration. So what we will obtain then, so we will have this Wm nearly equal to 4 times this HML whole square rho E m, okay, and divide by IH cross square. So integral will carry only sine square omega dash t by 2 divide by omega dash square d omega dash. Now, the most contribution to the integral that we have here, it comes from the values which are very close. It comes from the values of omega, which are close to omega dash. At the same time, on the other hand, we understand how to do this integral from minus infinity to plus infinity. And for this, we have the integral minus infinity to plus infinity sine square x by x square dx is equal to pi. So we can use this value of this integration for this integral. So therefore, what we can do is we can write an approximate relation based on this equation by setting this x equal to omega dash t by 2. So if we set this x equal to omega dash t by 2, what we will have is this transition probability Wm will be nearly equal to 2 pi by h cross, and you will have the matrix element HML dash whole square and rho E of m. Now, this formula that we have obtained here, this formula is called as Fermi golden rule. Now, this is called as Fermi golden rule, and it's used to calculate the transition probabilities per unit time when considering the optical properties of solids. Not only solids, it's equally plausible and explicitly plausible, including the Raman scatterings. And if you think about it, I mean, suppose if the initial state is a discrete level, if we have some initial state and this initial state is a discrete level, if I go down this thing to an example, say a donor impurity level, and the final, suppose this is the initial state, and the final state is a continuum, and there is a final state, and this final state is a continuum, and this I should stand it from, I should choose this as continuum, because I can choose this as conduction band and some single state in the valence band. And then this Fermi golden rule, as we have written it here in this equation, what it does is it yields the transition probability per unit time, and rho, and this rho em is interpreted as density of the final states. And likewise, suppose if the final state is discrete, if we think the reverse, I mean, if the final state is discrete and the initial state is a continuum, then this Wm that we have, it also gives the transition probability per unit time. Only in this case, this rho Em is now interpreted as the density of initial states. In the previous case, it was referred as the density of the final states. if you have a transition, if you had a transition from discrete to continuous state, then it was called as density of final states. And if you have the reverse, if you have from continuum to the discrete, then this rho em is called as density of the initial states. Now, if the transitions of interest are between the continuum of initial states and the continuum of the final states, if we have a situation like what I'm trying to tell here is that if we have a transition between the continuum of the initial states and the continuum of the finals, then this Fermi golden rule must be interpreted in terms of a joint density of states. Where from the initial and the final states they are separated by photon energy. They are separated by photon energy, h cross omega, inducing the transition. Now, at the same time, if we try to deliberate our discussion upon to this point and introduce the basic concept behind Fermi golden rule, that is, it provides an understanding of each term in this WM that we have. It provides separately, each term is explicitly providing information and its relation to the uncertainty principle. It's discrete in nature. And for further interpreting Raman spectra, we need to consider first order one phonon scattering process as well as second order two phonon scattering processes. Therefore, to describe Raman processes, we certainly have to consider the typical second order and higher order perturbation theory. And at the same time, while we start in an initial state, scatter into one or more intermediate states before scattering back to the final state. I mean, the expression for the Raman intensity that's obtained by these higher order perturbation processes, the workout for these processes is very cumbersome. They are quite laborious. At the same time, it does not add new physical insight, and such derivations, such laborious derivations they can be found in some standard books of quantum mechanics. I mean, in short, by increasing the order in the perturbation theory, one matrix element and one more term in the denominator will be added, and what we will have, we will come up with a summation over all possible intermediate states in writing down the transition probabilities that can